Alcohols contain the hydroxyl group, which is an OH group. Now the difference between the hydroxyl group and the hydroxide group, which is also OH, is the hydroxide group is an ion, and it's bonded ionically to some kind of cation, like the sodium ion, sodium hydroxide. The hydroxyl group is bonded covalently to other things, typically carbon atoms. While the hydroxyl and hydroxide are both OH, hydroxide is OH minus, it's an ion. The hydroxyl group is bonded covalently. Low molar mass alcohols, particularly, as opposed to high molar mass alcohols, are soluble in polar solvents due to the polar nature of that hydroxyl group. Oxygen is much more electronegative, and so that hydroxyl group is polar. You might have learned in an earlier chemistry class that like dissolves like, that is, polar substances like water and something polar like a low molar mass alcohol will mix well. All alcohols have higher boiling points than their parent alkanes due to the hydrogen bonding forces between adjacent molecules' hydroxyl groups. Primary alcohols have one R group, secondary have two, and tertiary have three. At the bottom of the page, this alcohol has one R group. When we say an R group, typically we're referring to some sort of hydrocarbon something or other, not a hydrogen, most often. When I think of R, I think of the rest of the molecule. So the one at the bottom of the page is a primary alcohol. The one to its right has two R groups. That's a secondary alcohol, and the one in the lower right corner is a tertiary alcohol. A primary alcohol is not one that always has a single hydroxyl group, and a secondary alcohol does not necessarily have two hydroxyl groups. Tertiary necessarily have three hydroxyl groups. No, primary, secondary, and tertiary refer to the number of R groups, not the number of hydroxyl groups. So let's name alcohols. Without being redundant, specify the location of the hydroxyl group or groups. The suffix is "all." The OH needs to take the lowest possible number, so the hydroxyl group takes precedence over everything else. You want to use di or tri right before the "all" suffix if you have two or three OHs. Let's try the one on the right side of the screen first, 1-propanol. I'm first going to draw a 3-carbon chain. That would be the prop part. And then to carbon number 1, I need to attach my hydroxyl group. Now remember, we can number this from either the left or the right, and here I chose to number 1 from the right. How about the one in the lower left here? Here we have 2 hydroxyl groups, so this is going to end in diol. Then we have 1, 2, 3 carbons in the chain, so this will be prop something, propanadiol, and then we have to specify the location of those OH groups. Those are both attached to number 1, so this molecule is going to have the name 1,1-propanadiol. If we had something called 1,2-propanadiol, then one of these hydroxyl groups would be attached down here to this carbon number 2. How about the next one? 3-ethylphenol. Phenols are alcohols. There's a phenol. By definition, this carbon right here is carbon number 1, so now we need to just attach an ethyl group to carbon number 3, like so. And in the lower right, 3-ethyl cyclohexanol. Let's draw a cyclohexanol molecule, and then we need to put an ethyl group off of carbon number 3. You can see that while they are similar, they are not identical. 3-ethylphenol down in the bottom of the screen in the middle, and in the lower right corner, 3-ethyl cyclohexanol. The difference being, if you look at the 3-ethylphenol, there's only one hydrogen hanging off of this intersection. There's one hydrogen hanging here, there's one hydrogen hanging there, there's one hydrogen hanging there. In the case of 3-ethyl cyclohexanol, there are two hydrogens hanging off right there, two hydrogens hanging off that carbon, two hydrogens hanging off that carbon, two hydrogens hanging off that carbon, and in fact, one hydrogen hanging off of this carbon, and one additional hydrogen that's not shown hanging off of this carbon right here. As you might remember, this benzene-like ring is a planar ring, whereas this cyclohexanol ring is not planar. It zigs up and down in maybe a chair sort of configuration, or possibly kind of a boat. In any case, they're similar but not the same molecule. The name of this molecule ends with 1-hexanol, so let's draw that out. Then to carbon number 5, let's attach a bromo group, and to carbon number 6, a chloro, and to carbon number 2, a propyl. Notice that the name of this compound does not actually have the longest chain of carbons. In other words, this propyl group is not part of the longest chain, and that's because this hydroxyl group, by definition, has to be hanging on to the longest chain. So this propyl group becomes a substituent. Let's try one more. Here we have 3 hydroxyl groups, so the name of this one is going to end with triol, and then we have a cyclopentane, sort of a shape, cyclopentanotriol. Then we need to specify the location of these hydroxyl groups, and we want to use the lowest possible numbering system, and that would be numbering this carbon, carbon number 1, and then this one number 2, number 3, and number 4. So this one is going to be called 1,2,4 cyclopentanotriol.